Okay, let's dig into this pretty serious weather forecast targeting Western Europe for early November 2025. We've got quite a bit of information here pointing towards, well, prolonged heavy rain. And our goal today, really, is to understand the two key things making this happen: the ocean fuel and the atmospheric engine driving it.
Exactly. And starting with that fuel, the foundation here is it's really exceptional ocean warmth. You mentioned the Med having its warmest first half year on record in 2025, which is true, but strategically, it's the North Atlantic heat that's crucial.
Oh.
That area had its third warmest January to June, and critically, the bit southwest of the UK, right in the path. Sea surface temperatures, SSTs, are up to 2 degrees Celsius above normal. That's a huge reservoir of heat just sitting there.
Right, 2 degrees. Now, we hear about warming oceans a lot. Why is this specific anomaly right there so potent? Does it fundamentally change things?
Oh, it absolutely does. Think of it maybe like heating water on a stove. The hotter the water, the faster it evaporates, the more steam you get.
Okay, makes sense.
The atmosphere is similar. There's this principle, the Clausius-Clapeyron relation. Basically, for every 1 degree Celsius warmer the air gets, it can hold about 7% more water vapor.
Ah, okay, so with your 2 degrees anomaly, quick calculation.
Yeah.
That's roughly 14% more moisture the atmosphere can physically hold, even before a storm forms.
Spot on. It's like preloading the atmosphere. You're essentially giving any incoming weather system a much, much bigger moisture budget to work with.
So it turns a regular storm system into something with potentially extreme rainfall.
Precisely. The potential for high-impact flooding goes way up just because of that initial moisture load.
All right, so that's the fuel sorted. Immense potential energy stored as water vapor. Now, what's the atmospheric engine, the mechanism actually delivering this? You described this specific setup, this synoptic pattern, a dipole.
Yeah, that's a good way to put it. You've got this deep, powerful, low-pressure trough digging down over the eastern Atlantic and western Europe. And then, crucially, parked right next to it over the central North Atlantic is a really strong, persistent, high-pressure system, a blocking high.
And the blocking part is key here.
It's everything. That blocking high acts like a giant wall in the atmosphere. It just sits there. It prevents that trough and the associated weather from moving eastward across Europe like it normally would.
So it gets stuck.
Pretty much. It locks in this persistent flow from the southwest. Think of it as a continuous atmospheric river or a fire hose.
Okay.
Constantly drawing on that warm, incredibly moist Atlantic air and directing it straight at Western Europe for days.
And that persistence is what escalates the risk from just rain to serious flooding.
Exactly. It's not just one storm passing through, it's the relentless nature of it.
And just for context, for people who track the larger climate patterns, this setup, it basically looks like a strong negative phase of the North Atlantic Oscillation, the NAO.
That's the climatological box it fits into, yes. A strong NAO means that typical west-to-east jet stream flow is disrupted. You get these slower, meandering north-south flows instead. Holds that fire hose steady. And one other thing to note, there's likely an extra energy boost from the remnants of ex-Hurricane Melissa.
Oh, right.
Which are tracking northwest of the UK. It sort of injects a bit more spin and latent heat into that trough, kind of turbocharging the whole system.
Okay, so potent fuel, persistent engine, even a bit of a tropical boost. Let's talk impacts. Where is this likely to hit hardest? The risk isn't uniform, is it?
No, definitely not. The biggest threat is always where this moisture-laden air interacts with topography, mountains.
Orographic lift forces the air up, it cools rapidly and just dumps the moisture.
Exactly. And with this setup, we're looking at the potential for multi-day rainfall totals in the hundreds of millimeters in specific hotspots.
Hundreds. Wow. Okay, where are these hotspots likely to be?
The main areas are the big mountain ranges facing that southwesterly flow. So the Pyrenees, the Alps, especially those south-facing slopes, think places like Bovec in Slovenia, also the Apennines in Italy, the Dinaric Alps across the Balkans, and parts of western Iberia, too.
That's a really important point, especially for you listening. You might remember seasonal forecasts back in, say, August that actually suggested a drier than average autumn for parts of Central and Southern Europe. But this single, intense, persistent event can completely overwhelm that seasonal average. It really shows how one high-impact event can define the risk in our changing climate.
Absolutely. It highlights the difference between climate outlooks and specific weather threats, and these levels of rain over multiple days they bring secondary risks.
Like infrastructure damage.
Yes, exactly. We saw this in the Western Europe floods in 2021. You get cascading failures, transport links cut, power outages, problems with utilities. These impacts can last long after the rain stops.
So pulling it all together, we're really looking at what scientists call a compound event. It's not just one factor, is it?
No, it's the alignment. You've got the extreme ocean heat providing the fuel, you have the persistent blocking pattern providing the delivery mechanism, and you even have a little extra kick from tropical remnants, all happening at the same time, reinforcing each other.
And perhaps the final thought for you to consider is that this isn't just some random freak occurrence. This kind of high-impact compound event driven by unusual ocean warmth and persistent atmospheric patterns is precisely the sort of thing Climate Models Project will become, well, more common, more intense as the world continues to warm. It's a concerning glimpse, perhaps, into a future normal.